Welcome back to the Deep Dive, the place where we really try to take that fire hose of technical information.
Yeah.
The articles, the papers, complex requirements, and, well, boil it down into the essential knowledge you actually need.
Yeah, the actionable stuff.
Exactly. And today, we are tackling something super critical. It's a skill that, honestly, separates the overwhelmed designer from the one who's really got a handle on things. Back-of-the-envelope estimation.
Right. This is all about getting that technical knowledge quickly, but also thoroughly, especially when you start dealing with scale. Big scale.
Yeah, scale changes everything.
It does. And whether you're, designing the next massive service, or maybe you're just in a high-stakes meeting, and assumptions are flying around, you need a quick way, a reliable way to figure out, is this even feasible?
So today's deep dive is really focused on that toolkit, right? The system designer's shortcut for figuring out capacity, performance requirements efficiently.
That's the goal, equipping you with that essential shortcut.
And let's be clear, we're not talking about just like random guessing here.
Yeah.
This method, BOE as they call it, it's actually a formalized process.
Very much so. You mentioned Jeff Dean from Google earlier.
The Google senior fellow.
Yeah.
His definition is great.
It is. He called these calculations estimates created using a combination of thought experiments and common performance numbers. The whole point is to quickly see which designs are even, structurally sound. Are they even in the right ballpark?
Right. Ballpark is the key word.
The beauty of it is the efficiency. You're not trying to get mathematically perfect answers down to the last decimal.
No, not at all.
You're aiming for directional correctness.
Okay.
Is it roughly right? Within an order of magnitude. Because look, if your quick calculation says your design needs, 10,000 servers.
And the budget's for 100?
Exactly. Instantly, okay, back to the drawing board. Need a whole new architecture. It saves massive amounts of time.
Okay, so our mission for this deep dive then is to lay out that foundational toolkit.
Mm-hmm.
It sounds like we're basically learning the physics of computing here.
That's a great analogy, actually. You wouldn't build a skyscraper without knowing about gravity, right?
Of course not.
And you can't really build a massive distributed system without knowing these fundamental constants, things like scale, speed, and, crucially, reliability.
Got it. The physics of computing. I like that.
And our source material, it really highlights that for BOE to work, there are 3 foundational concepts you absolutely have to internalize. They're like the bedrock.
Okay, lay them on us.
Yeah.
The essential 3.
Right. First, the power of 2. This is all about how data, volume, and memory space get calculated. Really fundamental.
Okay, power of 2.
Second, latency numbers. This gives you that mental model for how fast, or more often, how slow computer operations actually are across different parts of the system.
Latency. Got it. And
Third, availability numbers. This is where we quantify reliability using those famous 9s, 99.9, 99.99, that sort of thing.
the 9s.
If you can really master these 3 constants, honestly, you can tackle almost any scale challenge with a lot more confidence.
Okay, power of 2, latency, and availability 9s. Let's dive in. All right, let's kick off with the first part of that toolkit, scale and speed. We start with the power of 2. Now, expert speaker, you hear this, and, we're designing systems handling petabytes, exabytes, insane amounts of data. Why do we need to get bogged down in, the difference between a bit and a byte? Seems basic.
It seems basic, but it's absolutely foundational because every single calculation, no matter how huge the final number is, it starts with that basic unit.
Okay.
And if you get that unit wrong, or maybe the scaling factor wrong, even by a tiny bit, that error doesn't just add up, it multiplies. Billions, trillions of times over by the time you're talking petabytes or exabytes.
Okay. So the error scales up massively.
Massively. So yeah, we start small. We know a byte is 8 bits. Simple enough. An ASCII character, standard text, that's about 1 byte. But here's where people often trip up in system design. It's the difference between powers of 10, which we use in everyday life, and powers of 2, which computers use.
The 1000 versus 1024 thing.
Exactly. That's the first critical trap in BOE. In networking, sometimes marketing materials, a kilobyte often just means 1,000 bytes. Power of 10. Simple.
Yeah, seems easier.
But in system design, especially when you're talking memory, storage addressing, anything close to the hardware, you have to use the base 2 system. So a true kilobyte, or maybe more accurately, a kibibyte. Kibi, that's 124 bytes. 2 to the power of 10.
Okay, wait. Why is that tiny difference, 24 bytes? Why is it so important? Can't we just round down to 1,000 for simplicity in these quick calculations?
You'd think so, but no. Because computer hardware, the way it addresses memory, the way storage is laid out, it's all based on binary. Powers of 2 are inherent in the architecture.
Okay.
So if you consistently use 1,000 instead of 124 as your multiplier, when you're calculating storage for, say, a petabyte scale system,
Yeah.
that error just keeps compounding.
Right. It's not just 2.4% once.
No, it's 2.4% compounded at each step. By the time you get up to petabytes, your calculation using 1,000 is actually off by about 7%, maybe more, depending on the exact scale.
7%. That sounds like it could actually matter.
It absolutely matters. A 7% error on a petabyte system could mean you've ordered, I don't know, dozens of extra storage racks you didn't need, or worse.
Worse.
You under-provisioned. You thought you had enough space based on your 1,000 base calculation, but the reality of 1024 means you run out of disk space way sooner than expected, leading to crashes, data loss, big problems.
Okay, I'm convinced. 1024 it is. That makes the scaling crystal clear. We use 1024 as the multiplier moving up. Kilobyte, kibi, megabyte, megabyte, terabyte, terabyte, petabyte, AAB. Remembering that AB part helps keep it straight.
Exactly. That foundational knowledge using the right power of 2 ensures that when we estimate something huge later, like 55 petabytes, that number is actually grounded in the physical reality of the hardware, not just some rounded guess.
Grounded in reality. Got it. Power of 2 is locked in.
Excellent. So understanding volume is step 1. Step 2 is time, speed, latency.
Right. We need that designer's mental model of time. Our source material talks about those classic numbers from Jeff Dean, but updated for, like, the 2020 computing world.
Yes. And this latency data, honestly, it's like the universal cheat sheet. Every single system designer should have these rough numbers just burned into their brain.
Why burned in?
Because the differences in speed between different operations are just, they're mind-bogglingly vast. If you treat an operation happening in CPU cache the same way you treat something going over the network or, God forbid, to a spinning disk,
Yeah.
your system is doomed. It just won't work realistically.
Okay, so the scale of difference is the key. Let's quickly just nail the units, then jump into that comparison. We've got nanoseconds, NEOS, that's $10. See? Then microseconds, AMS, then milliseconds, $3.
Correct. But again, the absolute definition isn't the point as much as the relative difference, the orders of magnitude between them. Let's try that analogy you mentioned, scaling time up.
Right. Let's say 1 nanosecond, which is roughly a CPU cycle, performing one simple instruction. Let's scale that up to feel like 1 second of real time.
Okay, 1 ns equals 1 second in our mental model.
So what happens?
Well, fetching something from the super fast L1 CPU cache, maybe half a nanosecond, that feels like half a second, still lightning fast.
Okay.
But then, just referencing main memory, DRAM, which is maybe 100 nanoseconds in reality.
Yeah.
In our scale time, that's 100 seconds, almost 2 minutes, just to get data from RAM.
2 minutes. Okay. Already seeing a big jump?
Now hold on, let's talk storage. Accessing data from a local solid-state drive, an SSD. Maybe that takes, say, 100,000 nanoseconds or 100 microseconds.
Okay, 100,000 seconds in our model.
Yeah. That translates to over 27 hours, nearly a day and a half, just to read from a fast local SSD.
Wow. Okay. And the old spinning disks, the HDDs.
The magnetic hard drives. The killer is the seek time moving the physical read head. That's maybe 10 milliseconds, which is 10 million nanoseconds.
10 million nanoseconds. So 10 million seconds in our analogy.
Do the math. That's roughly 115 days, almost 4 months.
4 months versus 1 second for a CPU operation.
Exactly. That's the takeaway. The difference between memory speed and disk speed isn't just large, it's almost incomprehensible without this kind of scaling. And misunderstanding that is catastrophic for design.
That massive time penalty, the 4 months for a disk seek,
Yeah.
it basically dictates the entire architecture of caching, doesn't it?
It dictates almost everything about performance. And it leads directly to one of the most critical rules in system design. Avoid disk seeks like the plague, especially random seeks.
At all costs.
At almost any cost. You should design your system to do pretty much anything else. Complex calculations, compress data heavily, even make a quick call across the local network before you force a random disk seek. The time cost is just too astronomical.
Okay, avoid disk seeks. That's clear. Now, what about compression? You mentioned that. The latency numbers suggest compression algorithms are surprisingly efficient.
They really are, especially compared to I/O. Simple compression algorithms like zlib or snappy, they are incredibly cheap in terms of CPU cycles.
Cheaper than sending data.
Way cheaper than waiting for I/O, especially network I/O. Think about it. The CPU cycles needed to compress a chunk of data are usually tiny compared to the time it takes to push all those uncompressed bytes through a network pipe, which is often the bottleneck.
Ah, so bandwidth is usually the limiting factor, not the CPU thinking time for compression.
Precisely. So it's almost always faster to spend a few CPU cycles shrinking the data before you send it. Reduce the volume, reduce the transfer time.
So if I'm transferring, say, a 1 megabyte file across the network,
It's not the CPU work for compressing it down to maybe half a megabyte that's going to slow you down. It's the waiting time for that full megabyte to physically cross the wire if you didn't compress it.
that makes sense. The CPU is just so much faster than the network or disk.
Orders of magnitude faster for this kind of task. So the design implication is huge. Compression should basically be your default. Use it almost everywhere in memory caches, before writing to disk, definitely before sending over the network. It's usually a net win.
Default to compression. Got it. Okay, one last piece on latency. Geography, distance. We build global systems. Latency is limited by the speed of light, right? So what are the real-world numbers? What's the cost of sending data across a country or an ocean?
Yeah, even light speed isn't instantaneous over long distances. A typical round-trip time, RTT sending a request and getting a response back across a continent, say New York to San Francisco, you're looking at roughly 50 to 80 milliseconds. Maybe a bit less, maybe a bit more, but in that ballpark.
50 to 80 meters coast to coast and across the pond, New York to London.
Easily hitting 100 to maybe 150 milliseconds for that round trip.
150 milliseconds. Okay, let's plug that back into our nanosecond equals a second analogy. 150 meters is 150 million nanoseconds.
So in our scaled time, that's 150 million seconds, which is, wait for it, nearly 5 years.
5 years. For one round trip across the Atlantic.
That's the scale of the delay. So think about user experience. If your user in London clicks something, and the system needs to do a synchronous database lookup in New York before it can even start rendering the page, they are waiting at least 150 milliseconds just for the network packets to travel back and forth. That's before any server even thinks about processing the request.
That's an eternity in web performance terms.
It is. And it's why you simply cannot design systems that rely on real-time, synchronous communication across large geographic distances for critical path operations. The physics just forbids it. You absolutely must use things like content delivery networks, CDNs, regional data replicas, asynchronous processing. You have to assume network latency is your biggest enemy after disk seeks. Design around it.
Okay, that deep dive into speed, or rather the lack of speed for disk and distance, leads us perfectly into the next essential tool, availability. How do we make sure the system we're designing, which is fighting against slow disks and cross-continent delays, actually stays up and running?
Right, we need to quantify that reliability, and we do that using high availability, or HA, usually measured in those nines.
Eins, okay.
It's basically the metric that defines how consistently the system is operational and available to its users over a significant period, usually a year. And it's critical because downtime almost always means lost revenue, lost trust, or worse.
And this isn't just an internal goal, right? It often gets formalized in contracts.
Exactly. That's the service level agreement, the SLA. It's the formal promise between a service provider, maybe a cloud vendor or a SaaS company, and the customer. It defines the minimum acceptable uptime.
And if they fail.
Usually there are penalties, financial credits, refunds. It makes availability a hard business requirement. And if you look at the major cloud providers, AWS, Google Cloud, Azure, their standard SLAs for many core services are typically set at 99.9% or often higher. 3 nines or more is common.
Okay, but let's get into quantifying that, the power of nines. This is where we translate that percentage into actual concrete minutes or hours of downtime allowed per year.
Yeah.
This feels like where the architectural choices really start to bite.
Absolutely. This is where the aha moment happens for many designers when they realize the implications. Let's start at the lower end, just for context. 2 nines, 99% availability.
99%. Sounds pretty good on the surface, right? Only 1% downtime?
It sounds okay, but think about a year. 365 days. 1% of that is roughly 3.65 days. Almost 4 full days of downtime spread across the year.
4 days. Okay, yeah, for anything remotely critical, that's terrible.
It's usually completely unacceptable for any serious external-facing service. Maybe okay for a non-critical internal tool, perhaps, but generally 99% is not a serious target for high availability.
All right, so let's move up to the more common benchmark you mentioned. 3 nines, 99.9%.
Okay, adding that third 9 makes a huge difference. 99.9% availability cuts that allowable annual downtime dramatically. It goes from 3.65 days down to about 8.76 hours per year.
8 3/4 hours.
Oh,
That feels more manageable.
it is. And this level, 3 nines, is a very common target for many commercial applications, especially those that can tolerate some planned downtime for maintenance, maybe overnight or on weekends. It's achievable without insane complexity,
Hmm.
but it still requires robust design.
Now, here's where I want to push a bit. 8 hours a year. That's like, what, 45 minutes a month on average?
Yeah.
Why is the jump to the next level, 4 nines, 99.99%, considered so much harder and more expensive to engineer? It doesn't sound like that much less downtime on paper.
But it is, because you're fundamentally changing how you deal with failure. 4 nines, 99.99%, reduces your total annual downtime budget to just 52.6 minutes, less than an hour, for the entire year.
52 minutes. Okay.
Think about what that means for recovery. With
Yeah.
8 hours, 3 nines, if something breaks, maybe a server dies, you probably have time for someone to get paged, log in, diagnose the problem, and manually fix it or fail it over within an hour or two.
All right, there's some breathing room.
With only 52 minutes for the whole year, that manual approach is gone. You cannot rely on humans reacting in time. Any significant failure needs to be handled automatically, instantly. Mean time to repair, MTTR, has to approach 0 for many failure types.
So the engineering challenge isn't just building more reliable components, it's building automated recovery systems.
Precisely. To hit 4 nines, you absolutely need things like automatic failover between redundant servers or services. You need redundancy across different physical locations like separate data centers or availability zones within a cloud provider. You need deployment strategies like blue-green or canary releases so that pushing new code doesn't risk an hour-long outage. You have to eliminate single points of failure everywhere. It's a major step up in architectural complexity and operational rigor.
Okay, that makes the cost jump clear. It's the automation and redundancy tax.
Yeah.
And then the pinnacle, 5 nines, 99.999%.
5 nines. Now we're in the territory of truly mission-critical systems. Think financial trading platforms, emergency services communication, maybe critical infrastructure control systems.
What does that translate to in downtime?
5 nines means your total allowable downtime per year shrinks to just 5.26 minutes.
5 minutes. That's basically continuous uptime. There's almost no room for error whatsoever.
Exactly. Achieving 5 nines is incredibly difficult and expensive. It demands not just redundancy across zones within a region, but often active setups across multiple geographic regions. It requires extremely sophisticated monitoring, automated fault detection, traffic routing that can bypass entire regions if necessary. You need rigorous testing, chaos engineering. The cost and complexity are often an order of magnitude higher than even 4 nines.
So understanding these nines isn't just about percentages. It directly tells the designer how complex, how redundant, and how automated their architecture must be to meet the business promise, the SLA.
That's it, exactly. It sets the entire tone for the design effort.
Okay, we've built this fantastic theoretical toolkit. Power of 2 for scale, latency for speed constraints, power of 9s for reliability targets. Now let's make it real.
Yeah.
Let's put it into practice with a capacity estimation exercise. We're going to try and apply BBOE to estimate the requirements for a hypothetical massive social media platform, something like Twitter, but using, simplified non-real data just for learning.
Great idea. This is where the theory hits the road. And the absolute first step, the most critical, and honestly the one people often gloss over, is clearly stating and writing down your assumptions.
Why is that so critical?
Because the entire estimate hangs on them. Your final numbers are only as valid as the assumptions you started with. If the assumptions are wrong or unclear, the estimate is basically useless. And documenting them allows others, and your future self, to understand the basis of the calculation and, importantly, how changes in assumptions would affect the outcome.
Makes sense. Build on a solid foundation.
Yes.
Okay, let's lay out the hypothetical assumptions based on our source material for this Twitter-like service.
Okay.
First, let's say 300 million monthly active users, MAU.
Got it. 300 MAU.
Second, assume 50% of those MAU use the service daily. So half are daily active users, DAU.
Okay. 50% DAU-MAU ratio. Common starting point.
Third, let's say users post, on average, 2 tweets per day.
2 tweets a day. All right.
Fourth, maybe 10% of those tweets contain media photos, videos, etc.
10% media attachment.
And finally, the business requirement.
Mm-hmm.
Data needs to be stored for 5 years.
5-year retention. Got it. Okay, those are our constraints.
Yeah.
They define the envelope for our back-of-the-envelope calculation. Everything we estimate should trace back to these numbers.
Right. Where do we start? Maybe throughput?
Yeah.
How many requests per second?
Yeah, query per second, QPS, is usually a great starting point. It answers that fundamental question, How busy are our application servers going to be? How many transactions do they need to handle every second? Specifically, let's focus on the right QPS first, the tweets being posted.
Okay. Step one, then, is figuring out the daily active users, the DAU. We said 300 million MAU and 50% use it daily.
Right. So 300 million times zero point 0.5 gives us 150 million daily active users.
150 million people using it each day. Okay.
Now let's figure out the total number of tweets per day. 150 million users times the assumed 2 tweets per user per day.
That's 300 million tweets generated daily.
Correct. Now, to get the average QPS, we need to spread those 300 million tweets across the total number of seconds in a day. How many seconds in a day?
24 hours times 60 minutes times 60 seconds.
Yeah.
That's 86,400 seconds.
Exactly. So we take 300 million tweets divided by 86,400 seconds.
Okay, 300,000, 86,400. Doing some quick rounding here. That's roughly 300,086. Maybe like 100,000.
Yeah.
30. Somewhere around 3,500.
Yeah, that's pretty close. Let's call it approximately 3,500 QPS. That's our baseline average rate of incoming write requests, new tweets being posted, hitting the system, assuming perfectly uniform traffic distribution.
3,500 writes per second average out. But traffic's never uniform, right? It spikes. Lunchtime, evenings, big news events.
Absolutely never uniform. And this is where Bowie needs that layer of practical experience or common sense. You must account for peak traffic. A standard kind of rule of thumb approach in Bowie for general consumer services is to apply a peak factor. Often, 2x is used as a starting point.
So double the average to estimate the peak.
Yeah, assume that at the busiest time of day or during minor surges, the traffic might be twice the average. So we take our 3,500 average QPS and multiply by 2.
Okay, 3,500 times 2 gives us 7,000 QPS. That's our estimated peak write load.
Exactly. And that number, 7,000 peak QPS, is incredibly important. It's one of the first major outputs of our estimation. Why? Because it immediately informs your infrastructure needs, especially your database scaling strategy.
How so?
Well, ask yourself, can a single typical database server handle 7,000 write operations every single second consistently?
Probably not. Especially if it's a relational database doing A to D transactions. That seems high for one box.
Right. It's very high for sustained writes on a single node for many database types. So if you know your chosen database system can maybe handle, let's say, 1,000 sustained writes per second per shard or instance,
then 7,000 peak QPS immediately tells you you need at least 7 database shards just to handle the tweet ingestion load.
Precisely. Just like that, BOE gives you a concrete minimum scaling requirement for your persistence layer. And remember, that's only for writes. Reads people viewing timelines are often 10x or even 100x higher than writes. So this 7K QPS is really just the tip of the iceberg, but it already forces a distributed architecture.
That makes sense. But let me challenge that 2x peak factor for a second.
Yeah.
For something like Twitter, news breaks, global events happen, celebrities tweet. Couldn't the peak be way more than 2x? Like 10x, 20x even for a short burst? Is 2x potentially underestimating?
That is an excellent point, and it highlights exactly why stating your assumptions is paramount. The 2x factor is a common general starting point for BOE when no specific peak characteristic is given. It covers typical daily variations.
But not extreme events.
Exactly. If the specific requirement was design a system to handle election night tweet volume or survive a World Cup final mention storm, then assuming only 2x peak would be naive and wrong. In that specific context, you would explicitly state a different assumption. Assume peak traffic during major events can reach 10x average for 1 hour.
And that would change the number drastically.
Absolutely. 10x would mean 35,000 peak QPS. And that number forces entirely different architectural decisions. You're immediately thinking about message queues like Kafka to buffer writes, probably a NoSQL database optimized for write throughput like Cassandra, massive caching layers everywhere, maybe even rate limiting.
Okay, so the 7,000 QPS from the 2x factor gives us the baseline capacity for normal peak operations. But specific requirements might demand adjusting that assumption upwards significantly.
Precisely. The process forces you to consider those scenarios. Okay, so we have a handle on throughput. Let's switch gears to the other big resource, storage.
Right. All those tweets, and especially the media, need to live somewhere. We assumed 5 years of retention.
And we assumed 10% of tweets have media. The source material suggested focusing on media storage first, as it usually dominates the volume.
Makes sense. Text is small, media is big. What assumptions do we need for data sizes?
We need rough sizes for the components. Let's keep it simple. Maybe the tweet metadata itself, the tweeted, the text, even if it's longer now than 130 chars, user ID, timestamp, etc. Let's bundle that all up and say it's maybe, generously, 200 bytes total. Relatively small.
Okay, 200 bytes for the text and info.
But the media attachment, the photo or the video clip, that's the heavyweight. Let's stick with the assumption from the outline. Assume an average size of 1 megabyte MB per media item.
1 megabyte average for photos and videos. Okay.
That 1 MB figure is what's going to drive our storage calculation. The 200 bytes of metadata is almost noise in comparison when media is involved.
Got it. So let's calculate the daily media storage requirement. How much new media data comes in each day?
Okay, we start with our daily active users, 150 million.
Times 2 tweets per user per day.
Right. Times the 10% of tweets that have media.
Times the size of that media, which we set at 1 MIDI.
Exactly. So the calculation is 150 million, 2 tweets user, 0.10 for 10% media, 1 MB media.
Okay. 150 million 2 is 300 million, times 0.1 is 30 million. So 30 million, 1 megabit, that's 30 million megabytes per day.
Right, 30 million MB per day. Now let's convert that to more standard storage units. How many MB in a GB?
Roughly 1,000, or
Right.
1,024 to be
Yeah.
precise.
Let's use 1,000 for quick Bowie math here. It's close enough for the stage. So 30 million MB is about 30,000 gigabytes GB.
And how many GB in a terabyte?
TB. Again, roughly 1,000. So 30,000 gigabyte is 30 terabytes TD.
30 terabytes per day, just for the media uploads. Wow.
Yeah. Every single day, this hypothetical system ingests 30 TBB of new photos and videos. That's a significant amount of data flowing in constantly.
Okay, so that's the daily rate. Now we need to project that out over the 5-year storage requirement from our assumptions.
Simple multiplication now. We take the daily rate, 30 TB day, multiply it by the number of days in a year. Let's approximate that as 365.
Okay, 30 TB day, 365 days a year.
And then multiply that total by the required retention period, which is 5 years.
So the calculation is 30, 365, let's round again. 365 is close to 400 maybe. No, let's do 35 equals 150. Then 150, 365, that's like 150, 300 equal 45,000 plus 150, 65, maybe another 10,000, so around 55,000.
That's excellent. Bowie rounding. The actual number is 54,750. So 55,000 is perfect. And the unit. We started with terabytes.
So 55,000 terabytes, that's
Oh,
roughly to petabytes, right? 1,000 TV and a PB.
Exactly. Approximately 55 petabytes PB of total media storage required over that 5-year period.
55
Yeah.
petabytes. That number is just huge.
Yeah.
It really grounds the scale we're talking about.
It does. And let's quickly ground that 55 PB number itself. Think about physical hard drives. If you were buying, say, large 8 terabyte enterprise HDDs.
How many would you need for 55 petabytes? 55,000 TB drive. Roughly 7,000 drives.
Close to 7,000 physical drives. And that's just for one copy of the media data. That doesn't account for replication. You'll need at least 2x or 3x copies for durability. Doesn't account for file system overhead. Doesn't account for snapshot space or the storage needed for all the metadata, databases, indexes, logs, caches.
So the actual physical infrastructure footprint is much larger than even 7,000 drives.
Much larger. And this perfectly highlights why getting that initial power of 2 definition right was so crucial. If we'd made a mistake earlier, or if our assumption about average media size was off, say we assumed 5 millibeats instead of 1 millibeat average.
Then that 55 PB number would instantly jump by 5 times to 275 petabytes.
Right. And the difference between needing infrastructure for 55 PB versus 275 PB is not trivial. It's potentially hundreds of millions of dollars in hardware, data center space, power, cooling, and operational costs. BOE helps you see those massive cost implications driven by seemingly small initial assumptions.
That Twitter example really brings it home. The scale is immense, and BOE gives us a way to actually quantify it. But now, let's shift focus slightly to the process itself. Our sources really emphasize this. Getting the methodology, the way you approach the problem, right, is actually more important than hitting the exact final number with perfect precision.
Absolutely. This is probably the single most critical piece of advice, especially if you're doing BWA in a system design interview or a technical review.
Why is the process valued over the numerical answer?
Because the interviewer or the senior architect reviewing your plan, they aren't testing your mental arithmetic primarily, they're testing your thinking process. Can you identify the right questions to ask? Can you break down a complex problem into smaller, estimable pieces? Do you understand the key factors that drive scale users, requests, data size, time? Do you know the relative costs of different operations, like memory versus disk? That logical problem-solving approach is what they want to see. The final number is just the output of that process.
So focus on demonstrating good thinking, which leads to the next practical tip. Rounding and approximation. We did a bit of that just now. How aggressively should we round things?
Be pretty aggressive. As long as you maintain what we call directional correctness, getting the order of magnitude right, you should simplify the math ruthlessly.
Like the example in the notes, 99,987 divided by 9.1,
Exactly. Don't waste a second trying to calculate that precisely. Immediately turn it into 100,000 divided by 10.
which is 10,000. Easy.
Easy. And is it exactly right? No. But is it close enough for a Bowie calculation? Absolutely. It tells you the scale. Trying to get the exact answer of 10,987.58 is pointless and wastes precious time. Time is your most valuable commodity during estimation. Use it for thinking about the architecture, not fiddling with long division.
Right. Less friction in the math means more brain power for the design. Good advice.
The second absolutely critical rule for doing Bowie effectively, and we touched on this before, is clarity and documentation. You must write down every assumption you make, no exceptions.
It seems simple, but why is writing them down so fundamental? We know what we assumed. Right.
You think you do, but 5 minutes later, when you're deep into calculating storage replication, you might forget if you assumed 2 tweets per day, or 3, or 10% media, or 15%. More importantly, anyone else looking at your estimate needs to see the foundation.
Ah, so others can follow the logic.
Yes, and so they can challenge it constructively. If someone disagrees with your final 7,000 QPS estimate, the first place to look is the assumptions. Maybe they think 50% DAU is too low. Maybe it should be 75%.
And if the assumptions are written down,
You don't have to redo the entire calculation from scratch. You just plug in the new assumption, 75% DAU instead of 50%, and see how it changes the final number. It makes the estimate adaptable and debatable in a structured way. Your assumptions are the API to your calculation.
the API to your calculation. I like that. Okay, and related to clarity, another practical tip. Label your units. Seems incredibly basic.
It is basic, but it's amazing how often people forget it in the heat of the moment and how much confusion it causes. If you just jot down 55 on your whiteboard.
What does it mean? 55 megabytes, terabytes, petabytes, servers, QPS.
Exactly. Ambiguity is the absolute enemy of clear system design and estimation. Always, always write the unit. 55 PB, 7K QPS, 50 meters latency, 8 kilobit cache. It forces you to be precise about the scale you're talking about.
And it probably helps avoid mistakes when combining numbers later, right? Making sure you're not adding storage numbers to throughput numbers.
Precisely. It keeps you honest and clear in your own thinking as you build up the estimate.
Okay, so the process matters most. Round aggressively, document assumptions, label units. This really boils down to knowing what key things to actually estimate. For someone listening wanting to practice this, what are the typical targets they should focus on estimating?
That's a great question. Practice should center on the most common resources and bottlenecks in distributed systems. I'd group them into maybe 3 main areas.
Okay, area 1.
First, throughput. Practice calculating queries per second, QPS. Both the average QPS and, crucially, the peak QPS. Do this for different kinds of operations: writes, like posting a tweet, and reads, like fetching a timeline, as their characteristics are often very different.
Okay, practice QPS, average and peak, reads and writes. Second area.
Second, storage. Practice estimating the total storage needed over a given time period, like our 5-year example. And importantly, try to differentiate between different types of storage. There's often small, frequently accessed metadata, like user profiles, which might influence your database choice, versus huge volumes of blob data, like media files or logs, which points towards object storage like S3.
Right, so total storage, but also think about the type of data. And the third area.
Third, resources. This is about translating those abstract QPS and storage numbers into concrete infrastructure needs. The most common things to practice estimating here are cache size. How much RAM do you need for caching to be effective? And the number of servers or database shards required to handle the calculated peak QPS and total storage volume, considering redundancy.
Okay, so QPS, storage, and then translating that into cache size and server count. Practicing those seems like it would cover most common Bowie scenarios.
It would give you a very solid foundation for tackling almost any large-scale system estimation problem.
Well, we have covered a lot of ground in this deep dive on back-of-the-envelope estimation. We started by defining Bowie, really understanding it as a structured estimation process using Jeff Dean's ideas.
Right, setting the stage.
Then we built up that essential toolkit. The critical importance of the power of 2 for scale calculations, the mind-bending differences revealed by latency numbers, and the stark engineering realities imposed by the power of 9s for availability.
The core physics of computing, as you called it.
Exactly. And we put it all together, applying the toolkit to that hypothetical Twitter-like system, estimating a pretty significant 7,000 peak QPS for writes, and that just massive 55 petabytes of media storage over 5 years.
And hopefully the core message that comes through from all of this is really one of empowerment. Mastering these Bowie techniques, internalizing these numbers, it takes what seems like an overwhelmingly complex problem, designing for massive scale, and turns it into something you can actually get your arms around. You get actionable, directional estimates.
You move beyond just guessing if something is feasible.
Yeah, you start to know the constraints, you understand the boundaries imposed by the physical realities of computation, storage, and networks. It gives you confidence in your design choices.
Now, thinking back to that 55 petabyte storage number, it's huge. And we spent a good chunk of time earlier talking about latency, specifically how incredibly slow accessing disk is, particularly those random seeks, measured in months in our scaled analogy.
The 4-month seek time, yeah.
Yeah.
Still staggering.
So here's a final thought, maybe something provocative for you, the listener, to chew on, connecting those two parts. We have 55 petabytes of data, most likely stored primarily on slower, cheaper disk systems for cost reasons. Given the latency numbers we discussed, where reading from RAM is like 2 minutes in scaled time, but a disk seek is 4 months,
Okay.
how much of that 55 petabytes could your system actually read or realistically access within the time frame of a typical user interaction, which often needs to complete in, say, 100 or 200 milliseconds?
100 milliseconds compared to the latency of disk.
It's an absolutely minuscule fraction, right? You could maybe read a few contiguous blocks if you're lucky, but any random access across that 55 PB space within the 100 meters is basically impossible if you have to hit the underlying disk.
Impossible. So the provocative part is, what does that unavoidable time constraint tell you? If users expect to access potentially any piece of that vast data set relatively quickly, maybe finding an old photo, searching history, what does that fundamental latency mismatch force you to build into the architecture? It screams for massive caching layers, right? Maybe multi-tiered caching. It probably demands sophisticated indexing systems stored on faster media. It necessitates things like content delivery networks to keep popular data close to users geographically. It might even influence the choice of database or file system towards ones optimized for managing that scale and access pattern.
So the BAE storage estimate of 55 PB doesn't just tell you how many disks to buy. The combination of that scale with the known latency constraints reveals the inherent architectural complexity required. You have to build sophisticated caching and distribution systems. It's not optional.
It's absolutely not optional at that scale. The physics dictates it. BUE helps you see not just the size, but the resulting architectural imperatives.
That is the perfect place to leave it. A great thought to consider as you apply these BE principles to your own system design challenges. Thanks for joining us on the Deep Dive.
Always a pleasure. We'll see you on the next deep dive.